Hi all, good evening. So I have shared my screen. We have in our previous sessions we have seen GDB. What all commands are available in GDB. In today's session, we'll be looking into Codump. Uh, so what is a Codump? How can we use Codump using GDB? So what is a Codump? A Codump is a snapshot of memory at when the program is crashed. So whatever is present in the memory is stored in a file known as core. So whenever your program is crashed, it is stored the snapshot of memory. Snapshot of memory means the code segment, the data segment, stack segment, heap segment, and all the CPU registers. They all are stored in a file known as core. So core is a file which is being which the kernel will store the snapshot of memory when the program is crashed. This is known as code dump. So what is the use of codum files? Codum files allows us to save a crash for later. So we can save the file core file and we can later analyze why is the crash happening. And for embedded computers like we can it's not possible to debug on the computer itself because we'll not be having much memory. So you can just take the core file and you can analyze the code dump on a different computer. So these are the two use cases of code dump files. First use case is to perform crash analysis later. And if it is an embedded device, you can take the codem file and you can perform the crash analysis on a different device on the host computer. So let's try to generate a codem file. So see what is the problem in this code. Try to find out what is the problem in this code.
As null pointer is like you're assigning a null pointer to a
Yeah,
data.
we are assigning 10 to null pointer. So let's try to compile this code. So you need to provide -g and you say dot /source code and it is saying code dump. So when what we have understood till now is whenever your system your program crashes, it will generate a file known as core, which will have the snapshot of the program memory. So when I see that, I don't file any core file in my current folder. So this should be something we need to do more. So there, each and every process they have a limits. Each and every process will have various limits associated with them. So you can man set R limit will provide you more information about this. So core file is also one of the limits. So each and every process will have limits. So you can say man set R limit. So it provides you limits. So there are different resources like what is the maximum size of process virtual memory, what is the maximum size of core. So if the maximum size of core file is 0, then the code dumps will not be created. If it is non-zero, then the code dump file will be created. So what is the maximum CPU time limit in seconds? So there are different resources for each and every process. You can get the resource value, you can set the resource value using get R limit, set R limit APIs. So Linux provides you a utility known as ulimit. Ulimit -a will provide you all the information regarding what all resources are there, what are the values of each and every resource. So you can see the core file size is set to 0. We have seen in the man page when the core file size is 0, it means it will not create a codump file. So first we have to set the core file size to unlimited, using which you limit -c unlimited. Now let's verify it. Now you can see u limit -a unlimited. So we have changed the process limit of core file size to unlimited from 0. Now let's try to run our source code. Now let's verify whether core file is created. So you can see core file is created once as we have modified the core file size. So it is like almost 252K of size, 9.5K of utility, but you see the core file size is almost 252K. So we have now generated a core file. Core file is generated. Now what can I do with this core file? So core file can be examined with the GDB. So how to examine this core file with GDB? This is the command. GDB, the path of your binary, and then the path of your core file. So let's do it. GDB, path of our binary is source code, path of our core file is core. So say that. So now it is directly printing you the line at which the segmentation fault happens. You directly gave you information. No need of running the code, no need of saying backtrace, etc. Using core file, it is directly giving you information about the line at which the error happens. So line number five is ptr of 10 info locals. So ptr is null pointer, info registers. So you can do all those things. So any doubts in this process? It was very simple process, right? So first step is you have to make sure the size of the core file will be unlimited, and then you run your program. It will give you a core file. Then you say GDB path of your binary, so source code, and the path of your core file. That's it. It will directly give you the location where your source code is failing. Any problem here? Any doubts here? So it's easy, right? So this is when your program is crashing. So we have suppose one more program which is crashing. So do you think this program will crash?
It's an exception, right?
It will give an exception. Yes, because we are dividing 1 by 0.
Yes.
So let's run this code. Crash. So floating point exception, and it's saying codump. Now I can use this codump gdb crash core. And it directly gives say backtrace. So it has almost erased our frames.
Pajama, if you have other code down file means it will override it.
Yeah, it will overwrite it.
Okay.
So it is almost corrupting our frames itself. So suppose if I have a program and if I want to generate a codump of that program, codump is a memory of the particular program at that particular time. So codump is snapshot of the program memory at a particular instant. So we have seen codump when the program is crashing. But if a program is continuously running and if I want to generate a core of that particular file, can do it by using GDP. So suppose I have this program. So I'm running this program. So I need something which is running continuously. So this program will be running for 1 second, 1 minute. So I'm running this program, source code. To generate a code dump of this, you have to first attach to the PID and then you say generate core file. Optionally, you can give the file name and you say detach. So let's do it. Let's do GDB, need sudo permission. And let's run a shell command finding out the PID of source code and attach 2710. Now we have to say generate core file. So it has generated a core file core.270. Say detach. Quit it. You can see a new file has been created known as core.217 for this particular application. So it is continuously running. So we have not killed the application. We just took a snapshot of the memory at that particular time when we have run generate core file command. So we can now see using GDB a path of that. The path is GDB 11 source code, the core file. Now we can see backtrace. It gives us the, we can switch the frames, and it was sleeping at that particular time when we have created a core dump. It was at this particular instance when we have created a core file. So we can also create a core file when the program is also running using GDB. So I am running it again. There is another way by which you can create a codem file using kill command. If you send a sig abort signal to a PID, it will generate you a codem file. So kill, let's get the PID of that, ps-ef grep source code, and let's remove current core files. Yes. Now say kill minus s, sending a sig abort signal to 2738. Now let's see whether I have, this will kill the signal. So this is when it is sending the sig abort signal, this source code will receive the sig abort signal and it will abort the program, and your program will be core dumped. And now you have your core file again. So this is used. This is another way by which you can create a core dump file using. So if your program is stuck and you see your program is not doing anything, but it is continuously present in PS, you can just do a kill signal and take the codem file, and then you do a GDB and you can find out what is the line where it is running, which line is causing the problem. So if this can be used when your program is in hanged or freezed and it is not doing anything. So you can also dump core from within your program. Just you have to call abort. If you call abort from your program, you can generate a codem file. So these are the various ways by which you can debug an existing application. If it is crashed and generated a code dump, you can use GDB, or you can use GDB to generate a code dump file, and then you can debug it, find out line number where it was running, and examine the memory locations. So this is all about code dump. If you have any doubts here. So now we'll be looking into Linux before going into Valgrind and electric fence. We'll be looking into what all issues are present in Linux if we are using memory. So common memory issues in C programming are incorrect memory accesses. If you are trying to use variables which are uninitialized, if you're trying to access memory out of bounds, like you're trying to read -1 index of an array, or if you're trying to read 10th address of an array which is array of size of 5 members, and if you're trying to use after free, if you have a dynamically allocated memory and you're trying to use after free, that is wrong. If you're trying to use a local variable which is written by a function, double free, leakage. So these are the common memory issues in C programming. So let's try look in the sample codes. So what is the problem here? Is there any problem in the code? So here the local, we are using a local variable. The default value of a local variable is undefined. Means it's a garbage value. We cannot decide what is the value. It depends on what is the value present in the stack. And then we are trying to use that. So we cannot guess whether it can be 0 or it can be anything which is non-zero. So this function can generate either false case, it can generate true case. So the output is random. So the issue here is we are trying to use a variable which is uninitialized. So uninitialized variable issue. So let's try to run it. You're getting false case. So that variable is assigned to 0. So can I get an error if I compile it with GCC? So normal GCC compilation is not giving me an error. But if I use -wall, wall means enable all warnings. W is for warning, all. It will tell me this error. X is used uninitialized in the function. So GCC is giving you this error. So you have to add, if you want to find out this kind of errors, you have to add -WALL. So write overflow out of bound memory accesses. Write overflow means when you're trying to write into a memory buffer after its legally accessible location. Underflow is before its first legally accessible location. So similarly for read, when you're trying to read from the before its first legally accessible location, it is underflow. Overflow is after its last. It's after its last legally accessible location. So overflow, underflow. Overflow can be for write and read. Underflow can also be for write and read. So, so examples are for this. So see what happens in this code. Write underflow. I am trying to allocate memory of 8 bytes, and then I am subtracting 1 byte. I'm copying 8 bytes of information, and then I'm incrementing and calling free. Do you think this works? Will it fail? Will it crash? So I'm trying to write to a location before the actual memory allocated location. So it's an underflow. I'm trying to access before the first legally accessible location. So this is write underflow. So what will be the output of this? Will it crash? So let's see whether GCC is giving any bug for this kind of code. So GCC is not giving any bug for that particular code. It is giving for these functions malloc on free that can be removed by adding header file stdlib. So GCC is not giving any warning even if I add. So it is giving to some other functions, which is line number 9. It's saying set but not used. Okay. So now let's try to run it. So now it's saying double free or corruption because we tried to modify the malloc memory, which is not in our place, not in our access region. So it failed. Okay. Underflow is failing. So this kind of error is not detected by GCC. So you have to use some special tools to detect such kind of errors. So let's try other overflow. So in overflow, compile time memory is when you are allocating on the stack. So I'm trying to, I have an array of 5 members, but I'm trying to write up to 50. So this is overflow, right? Trying to access beyond its last legal location. So do you think this will fail?
Yeah, it will fail.
Let's look at like if I'm trying to do compile memory. Segmentation fault because we are trying to access, and I can just say GDB. It should give me a core file. Let's see because it has not given me a core file because the value is 0. This I can just say unlimited. and when I run it, it give me core file, and I can just say to core. So it is giving me inside RTLD. So we have modified, we have corrupted our stack. When you have corrupted the stack, you'll have something like this. So we try to access beyond our memory location and we have corrupted our stack. So this was when it was compile time memory. What about for dynamic memory, which we have created on using malloc? So we have a malloc of 8 bytes and we are using str copy and we are copying more than 8 bytes and then we are freeing the memory. So this is overflow. We are writing beyond its accessible location. Let's try whether this will give us any error. GCC, the GCC is not giving any error. So this is not failing because they may be, we are trying to write in heap and we are not overwriting any other memory location. So this may fail sometime, this may not fail sometime because it depends on what you are trying. If there is some other memory access being given to some other pointer. So if you are trying to overwrite some other memory location, this may fail. So, but this is a bug. You cannot say if it is not failed, this is not a bug. It is a bug. So we have seen write overflow, write underflow. Let's see some other thing. Read overflow and read underflow. So read underflow. So I have a malloc, 25 bytes. I have allocated 25 bytes. Then I'm assigning the pointer to original. Then I'm copying from destination to source, strlen of source. So I have copied it. And if the condition value is set, I'm modifying the value of x. I'm setting x and I'm saying dest minus minus. So what is the problem do you think here? What is the bug here? Is there any bug here? So orig is a character pointer pointing to the start of the memory location, right? And then we are subtracting it by 1 and then we are writing x. So we are trying to write x beyond our memory, before our memory accessibility, right? So it is a bug, right? So this is the bug here. See this, read overflow dynamic memory. So I have a malloc, 5 bytes, allocated 5 bytes. Then I have set it to all the 5 bytes to A. Then I'm trying to write beyond my memory space. So I'm writing secret. 5 equals to S, 6 equals to E, 7 equals to C, secret. And I'm printing the value of ARR. Now what I'm doing is I'm then trying to access more than my location. Like I'm trying to access 100 plus the pointer written by malloc, 10,000 plus the pointer written by malloc, and then I'm freeing. So this is a bug, right? So let's see this. Let's remove this. So read overflow dynamic memory. So I have only 5 bytes and I'm writing more than 5 bytes. And then I'm also reading beyond my memory, like 3. So you can see when I try to read, when I try to print ARR, it also printed what secret which I have given. And also the values 00. So this is a bug. You're trying to access the memory of the next portion of memory, right? You are trying to do a buffer overread. So if someone is using this memory, then you are able to read the memory values of that particular location. So ARR, when you say %ls, it will go until it reaches a null character. So hence it was able to print A for 5 times and then secret. So what is this other read overflow compile memory? So I have an array of 16, 16. I have set A to 16 bytes, all the A 16 bytes to A, all the 16 bytes to T, and then I am null terminating the temp variable. So what will be the value of ARR here if I print ARR? Any guesses what can be the value of ARR here?
I will print A and TTT.
So why it will print both A? It should only print A, right? ARR only has A. Why do you think it will print TTT also? When you print a %ls, it will continuously read the memory location until it sees null character. So we don't have a null character in this ARR of 16. All the 16 bytes are assigned A, and the next memory location is temp of 16. So we have again assigned it 6T. So let's see this. So it is printing A, T, all T's. So you can again verify it by using gdb./3 and break main run break read overflow compile memory continue info locals. So you have ARR and temp. I say next. I say next. I say info locals. Now you can see A is repeated 16 times. Next. T is repeated. Temp is repeated with T 16 times. Let's print the value of ARR. ARR is 70. Let's print the value of TMP. It's 80. So after 16 bytes, you have memory location for temp. I can use X to verify what all is present in ARR. X ARR will print me 4 bytes, but I need 16 bytes. So and I need in hex S, or I need in hex. So you can say 16 bytes. 61 is for ASCII value of A. 16 6 is 64 plus 1 65. But if I say 32, you can see it is continuously having A's first 16 bytes, and the next 16 bytes it is having T. So until it reaches the null character, it is continuously printing, and finally when it reaches the null character, it will stop. Printf will stop. So clear how why it is printing A and T because there is no null termination and you are trying to read overflow. This is the read overflow buffer. Read buffer overflow bug. So GCC is not reporting all these bugs. So we need special tools to find out such kinds of issues. So UAF is use after free. So if you are trying to use a memory pointer after it has been freed, then it is a bug. So this is also known as, if you're trying to use a memory pointer after free, we also call it as dangling point. So you see this code. So we have allocated memory. We have memset everything to A, and we have null terminated it. Then we have again allocated a new memory. We have free in ARR, but again we are trying to access ARR. So this is use after free. So ARR here is a dangling point. So let's compile this, whether it will fail or whether GCC will give any warnings when I'm trying to use after free. So GCC is not giving any warning for use after free bug. So again, we cannot find such bugs using GCC. So segmentation fault. So for this kind of bug, we need again tools like Valgrind, electric fence to detect such kind of bugs. So this is use after return. In this, you are returning a variable name, which is a local variable to this function. So this variable will be in the stack frame of this particular function. Once the stack is being removed, the memory for this can be given to some other function, and that is a wrong. It can be having some other value which is not the expected behavior. So once the return statement is takes effect, the name variable will be out of scope and the pointer to it is invalid. So this is the bug use after return. So let's try whether GCC will give warning for this. So GCC is giving warning for bug use after return. So you are returning a local address of a local variable. So you can find out such kind of bug using GCC. So there is no need of special kind of tool for finding out use after return bug. Let's move further. So double free, I think we already know what is double free. Double free is when you are trying to free same memory location twice. So if you're trying to free same memory location twice, you'll be having a bug which is double free. So here we are doing the double free. So let's find out whether GCC gives any error for bugs for double free. No, GCC is not giving any error for double free. So, but it will fail double free or corruption. So again, we have to use for this kind of bugs, we need to use Valgrind or electric fence. So what is memory leakage? Memory leakage is if you are unable to free the memory which you have allocated, it is just leaked. The memory is leaked as no one can use such memory. So if you are unable to free whatever memory you have used. So let's see one example. I'm having a leakage case one function and it is passing 32 as size and it is calling a function am leaky. Am leaky allocates the argument which you pass and then it just memset it, because if you don't memset it, compiler may optimize and just not allocate memory. So we have to memset it and then we are not freeing it. So first we try to leakage 32 bytes, then we are trying to leakage 1 MB. So 1 MB is 1024 bytes into 1024. So it's not 1 MB, it should be 1 KB. No, it's 1 MB. 1 KB. This is 1 KB. This is 1 again. So 1 MB. So let's find out whether GCC gives error for such kind of bugs. So GCC will not complain. So GCC is not complaining anything which we are doing for dynamic memory allocation. So for dynamic memory allocation bugs, you need to use Valgrind or electric fence. So you have leaked in the first case 32 bytes. In the second case, you have leaked like 1 MB. So this is okay. If you're leaking 0 bytes, 32 bytes or 1 MB, it's okay. But if you're trying to leak, like if your program is running in while one loop and it is continuously leaking 1 MB, then that is not good. Your memory, free memory will be, heap memory will be wasted. So let's see an example for that. So again, I have created a new function known as leakage case 2. This allocates 32 bytes, but we are doing this in a loop. How much? More than 1 lakh times. So 32 into 1 lakh is almost 3 MB. So we are leaking 3 MB here, but here 1 MB into 12. So 12 MB. So this function takes two arguments. First one is the size to be allocated and the loop count. So first we multiply, we allocate memory here. We are allocating memory here and we are calling it in a loop, am leaky. So let's see this. Before that, we need to know there is a tool, there is a utility in Linux known as free. The free utility displays in kilobytes the current memory used, the free memory available, and what whole memory available. So when you say free, it will display you total memory. I have a RAM of like 7 GB here. What is used? So 1 GB is almost used. How much is free? So free utility displays such kind of information. It also displays additional information like cache memory, shared memory, and swap information about swap partitions. So we are interested in this values. So total memory, what is the used memory, how much we is free. So if I'm only interested in the first line, so I can say free grep mem. So this will only display me the first line. It will remove the second lines. So when we allocate, so so in this code, we are again calling the same thing: system free grep mem before leaking, and then we are calling system free grep mem after leaking. So verify whether memory is actually leaking or not. So let's run this code. So in the first case where we have leaked 3 MB, so 32 bytes into this many loops, you can see the when you do free, the third portion is used. So when you subtract, when I subtract this, when I say calculator, subtract 1081548 minus 1077656. It's almost 3 MB. So I can divide it by 13892 divided by 1024, nearly 3 MB. So 3 MB is leaked. You can see from the used space when we leaked 3 MB. So it has, we can see that 3 MB is leaked. When we have leaked 12 MB, let's verify that. 1093624 minus 1081720. So again divide by 1024. So we have leaked nearly 12 MB. So suppose if this application is continuously running, then it may leak lot of memory of your RAM. So such kind of issues should be detected by using special tools like Valgrind. So we'll be looking into how we can detect such kind of issue using Valgrind. So any queries in this kind of issues, we have seen different kind of issues. We have seen uninitialized variables. If we are trying to use uninitialized variables, GCC will give such kind of errors. If you're trying to access out of bound memory, if you are trying to use after free or use after return, and if you're doing double free leakage, we will not be looking into this kind of issue for now. So mostly GCC will give you compile time errors like uninitialized variables, or if you're trying to use after return. But GCC will not give you errors for dynamic memory allocation like double free and leakages, etc. So we'll be using a tool known as Valgrind for that. So how can I use Valgrind for that? So any doubts still here? We can stop and we can have a discussion. So we can continue. So what is Valgrind? Valgrind is a debugging tool like GDB. Valgrind is also a debugging tool, and Valgrind is a wrapper around various tools which are used for debugging and profiling. So Valgrind is just a wrapper. There are number of tools. So using Valgrind, you can call any of the tools. So out of these tools, the best tool is known as memcheck. So memcheck is a tool. So Valgrind is a wrapper around various tools. Out of these tools, memcheck is there, and this is a tool which is used to find out memory leaks. So if you want to use Valgrind, you have to include debugging information. This means you have to compile your application with -G option. So let's do that. So let's first find out what we are doing here. First, we are allocating memory of 19 bytes, and then we are using the same pointer, and then we are allocating memory of 12 bytes. So what is the bug here? Can anyone guess what is the bug here? What we call this bug? Is it a dangling pointer or is it a memory leak?
It's a memory leak.
It's a memory leak because we allocated a memory and then we have not freed the memory, and then we reuse the same pointer to allocate the next memory.
Yes.
So let's try to find out using Valgrind whether it will report such kind of issues. So we need to compile with -G option to use Valgrind. Okay, we have compiled. So how can I use Valgrind? So what is the syntax? Valgrind, the tool which we want to use, the tool is memcheck, and we have to say leak check equals to yes and /, the executable. So Valgrind, which tool you want to use? As Valgrind is a tool wrapper around various tools, we have to mention the name of tools, and we say leak check yes. So let's do that. Valgrind. We have to say tool equals to memcheck leak check equals to yes and the utility. So now it is giving us information where the memory is lost. 16 bytes in one block are definitely lost in record 1, 1 of 2. So it is happening at line number 16. So let's look at line number 16. Cat minus n, I think. Line number 16 is this. So you are not doing free, hence it is giving us that error that 16 blocks are being free because you are not calling free after you call malloc. And then at line number 8, it is saying 19 bytes are lost. So let's look at line number 8. So line number 8 is this. So we are allocating 19 bytes and we are not freeing it, hence it is giving that error. So with Valgrind, we were able to detect memory leaks. So any problem, any queries here regarding the syntax? So let's move forward. So what is the bug here?
Overflow. It's
Read,
assigning more bytes.
yeah, read overflow. We
Yes.
have allocated memory for 12 integers, and then we are trying to access it more than, we are trying to access like up to 15
Yes.
integers.
Yes.
So let's use Valgrind to find out this bug. So Valgrind tool equals to memcheck, leak check equals to yes, and the executable. So it gave us the error at line number 6. So invalid write-off size. So you allocated 48 bytes, which is 12 into 4, but you are trying to access more than 48 bytes. So line number 6. So it said you allocated 48 bytes here, but at line number 11, you're trying to access more than the allocated memory location. So Valgrind is now able to also detect you read overflow bug. Find out what is the problem here. The previous bug was not read overflow, it was write overflow. You're trying to write.
Read underflow. This one.
This is not underflow, right? Underflow means before your first accessible location. I'm using, right? Before your first accessible location. I'm not doing ARR of -1.
Okay.
So what is the bug here?
It's a read overflow.
It's a read overflow because we have allocated 10 bytes, right? And so we can access up to 9 bytes, array of 9, right? So there's no bug here, right? Is there any bug? So indexes are only up to 9, right? Do you think any bug is there here? So let's use Valgrind. So you have array of 10 bytes, right?
In second for loop,
You're trying to print uninitialized variable, right? We have only initialized till ARR of 8,
hmm,
and we are trying to print till ARR of 9. So ARR of 9 is uninitialized because this is a local variable. So the bug here is uninitialized variable. GCC, let's see whether GCC gives this error. No, GCC is not giving that error. So Valgrind tool equals to memcheck, leak check equals to yes, 3. So it gave us so many errors. So it is saying trying to access uninitialized values at line number 10. So what is the line number 10? Cat minus n 3 or c. So you're trying to access uninitialized value at line number 10. So it give us the error. So using Valgrind, it is also giving us the uninitialized variable. So it is also saying if you add track origin equals to s, you can see where uninitialized values are coming from. So you can add this parameter and then you can get more information. So we were able to also detect uninitialized variable using Valgrind. So this is what kind of bug is this?
Double free.
here the PTR is already been freed, so you're freeing again the same memory.
So double free.
Yeah.
So that is a bug is double free. So let's compile it. So GCC is not reporting anything about double free. Let's use Valgrind. So Valgrind is saying at line number 9, invalid free. So you're trying to do free twice, so it is saying invalid free. So it is also saying 1 allocs, 2 frees. So that is wrong, right? Number of allocs, malloc should be equal to number of frees. So line number 9, line number 10. Line number 9 you were doing first free, and again at line number 10 you were doing second free. So this is the problem. So Valgrind is giving you information about double free also. So almost all the dynamic memory bugs are provided by Valgrind. Here,
Unassigned this thing.
which is uninitialized. PTR is allocated, we allocated a 10 bytes. It's not uninitialized, right? So you are trying to, you allocated 10 bytes of memory, and then you are reading 0 means standard input.
Standard input. Yes.
Yeah, you are reading from standard input 100 bytes and you are storing in PTR. Whereas PTR is only of 10 bytes. They have allocated only of 10 bytes. So which is the bug? We have write overflow, read underflow, write underflow. So we are writing, right? We are reading from standard input and we are writing into PTR more than the accessible memory location. So
Right.
this is write overflow. So GCC, now Valgrind. So it is asking for an input. So we have to give input. So it is giving it line number 6 and 7. Read points to unaddressable bytes. So let's verify that. Line number 7. So read is trying to point to unaddressable bytes. So it is giving write overflow error as well. So let's complete this. So this is what case? This we already seen in the first example.
X is uninitialized.
X is uninitialized. Let's see that. This is already reported by GCC, so not much useful. So GCC already reports it. Let's verify whether Valgrind is also reporting the issue. So it depends on uninitialized variable. So Valgrind also reports you about uninitialized variable. Line number 7. So you are trying to access uninitialized variable. So we have seen almost like all the memory bugs of Linux have been reported by Valgrind, and this is mostly used when you are having the dynamic memory allocation. So what are the advantages of Valgrind? It catches all the memory bugs on dynamically allocated memory region. So we have seen all those using uninitialized variable, read overflow, write overflow, use after free and use after return. We have not seen, but you can see, you can compile that code and you can check it out. Double free and leakage. So we can just see an example of use after free. So where is that use after free? So it is 5.c. Use after return. No. So UAF, use after free. Let's compile it and find out whether Valgrind is reporting this. So Valgrind. So it is reporting it. Invalid read of size. Right. Line number 39 in main function. In UAF function, it is line number 28. So let's verify that. So 28. So it is giving. We are trying to use after free. So it is also reported by Valgrind. Invalid read of size 1. So Valgrind is used to detect all the common memory bugs, leakages, double free. And you can also try the leakage example, which is present in that folder, to verify whether it is catching the leakage bug or not. You have not tried that. What are the disadvantages of Valgrind? Performance. So if you run your code in Valgrind, it will be 10 to 30 times slower. If you're running your program under Valgrind, it will be 10 to 30 times slower, and footprint will be more as memory allocation will take. So what happens is Valgrind will replace your malloc with its own malloc. So it will allocate a lot of memory for its own structures. So memory footprint will be more. So these are the disadvantages if you are using Valgrind. One is the performance, the other is a footprint. So any queries regarding Valgrind, it's very easy. You have to first recompile using -g option, and then you use memcheck tool. So there are different tools in Valgrind. For memory leak issues, we have memcheck tool. There is some catchy grind tool. There are other tools which we are not discussing. We only have to discuss about. We were only discussing about memory leaks. So any queries here? So in our next session, we'll be looking into electric fence tool, and then we'll be moving into system programming. So till now, we have been looking into various tools like GDB, Valgrind, and next session we'll be looking into electric fence. And in our future sessions, we'll be looking into strace and ltrace debugging tools. So if you have any queries, we can stop and we can have discussion on that. Else we can complete the session.